Let's see how to perform subtraction of floating point binary numbers. The process is very similar to addition. The assumption is that you've already watched my video on how to add together floating point binary numbers. Here's a summary of the process. First, we need to make sure that both numbers are normalized. Then, we need to make sure that the exponents are the same. In fact, we need to increase the size of the smaller exponent to match that of the larger one. Then, because we're performing subtraction, we need to negate the mantissa of the number that we're going to subtract to get the 2's complement form. Then we can add the mantissas together, just like when we're adding floating point binary numbers, and finally we can normalise the result if necessary. Let's see a couple of examples. Here's a problem. Both numbers are in floating point binary format. We're using 6 bits for the mantissa and 4 for the exponent, both in 2's complement. First, let's just write down the problem, and we'll convert both of the exponents into base 10 so we can see what we've got. Clearly they don't match, so we're going to increase the second exponent to match that of the first by floating the point 1 place to the left. This is our new problem. Now we're going to negate the mantissa of the second number. We do it by inverting the bits and adding 1. This gives us the 2's complement form. And now we can simply add the mantissas together. If there's a carry bit overflow, don't worry about it. We'll double check the result in a moment. This is our result with an exponent of 3. It's already normalised, so we should be there. But the way to find out is to double check. So the first number was 7. The second number was 3. So we're subtracting 3 from 7 to give us a result of 4. This is 4 in pure binary. And when we normalise it for a 6-bit mantissa and a 4-bit exponent, it checks out. Let's see another example. Again, both numbers are using 6 bits for the mantissa and 4 for the exponent, both in 2's complement. So let's just restate the problem, and we'll convert the exponents into base 10 so we can see what we've got. We need to increase the second exponent, so we can do that by floating the point 2 places to the left. Now remember, we've only got 6 bits for the mantissa, so we've lost a couple of bits from the right hand side of the mantissa. We've got a truncation error, and this might give us a problem later on. We'll see when we double check the result, but let's just continue for now. We'll negate the number that we want to subtract. Now we can add the mantissas together. There's been a carry bit overflow, but let's not worry about that. Our final result has an exponent of 4, but the result isn't normalised, so let's quickly do that. This is our result. But remember, we had a truncation error, so let's see what the impact was. The first number was 9. The second was 2.25, so when we subtract 2.25 from 9, we're expecting 6.75 as our final result. This is 6.75 in pure binary, and when we normalise it, this is what we get, and it's not the same as the result that we worked out when we performed the subtraction. Just to be sure, let's see what happens when we convert the number we worked out back into base 10. The number we calculated was 7, so you can see we've lost precision, and in fact the number is bigger than it should have been. You might have noticed that ironically we can represent 6.75 with a 6-bit mantissa, but the truncation error that happened during the process means that the final result is wrong. Here's a couple for you to try yourself. Pause the video now if you want to have a go, and I'll show you the solutions in just a moment. And here's the first solution. We've got an 8-bit mantissa and a 4-bit exponent this time, both in 2's complement. So this is the calculation we want to perform. We'll convert the exponents into base 10, and clearly we need to change one of them. We're going to increase the exponent of the second number to match that of the first, and we'll do that by floating the point to the left. Now we're going to negate the second number, the one we want to subtract, and we're going to add the mantissas together. The result has an exponent of 6, and we need to normalise the mantissa. So this is our final result. We haven't had any truncation errors during the process, so hopefully this is going to check out. Let's double check it. The first number was 34, the second was 16.5, so we're expecting 17.5. This is 17.5 in pure binary, and when we normalise it, we get exactly what we expected. And here's the second one. First of all, let's just state the problem. And now we'll convert the exponents to base 10. The one on the left is -1 and the one on the right is 3. But the number on the left isn't normalised, so let's do that first. That means we need to move the point one place to the right and decrease the exponent to -2. Now, to make the exponents match, we need to float the point of the negative number 5 places to the left. Notice how we're padding it with leading ones to make sure that the number is still negative. We're going to negate the number that we want to subtract, and we can add the mantissas together. Our result has an exponent of 3. It's already normalised. This is what we're expecting. So let's double check it. You might need a calculator to do this. The first number, when converted into base 10, is -0.8125. The second number is 4.5. Perform the subtraction, we're expecting a result of -4.6875. Here's -4.6875 in pure binary, and when we normalise it, it checks out. The subtraction process produced the correct result. To summarise then, first thing we have to do is make sure that both of the numbers are normalised. Then we need to make sure that the exponents are the same. In fact, we make the smaller exponent match the larger exponent. If we're performing subtraction, we need to negate the mantissa of the number that we're going to subtract, and then we can add the mantissas together. Finally, if necessary, we normalise the result. Watch out for truncation errors and representation errors when you're performing the process.